In this video, I'm going to show you how to find the determinant of a 3 by 3 matrix using Sarrus rule. So let's say we have this matrix A, which equals 1, 4, 3, 5, 2, 6, and 3, 0, 7. Our first step is to write the first two columns of matrix A to the right of the matrix. So I'll write 1, 5, 3, 4, 2, 0. And let me just copy this so I can show you a reference for later. So in Sarrus rule, this is how it generally looks like. We're just gonna multiply the entries along the diagonal and then add it up. So these sides we're gonna add it up, and then we'll subtract it by these diagonals. So they're negative. So this is just a picture of how a Sarrus rule would look like, but we can go step by step. So the determinant of matrix A is going to be, so we're just going to multiply the first line, and then we get 1 times 2 times 7 plus, so we have 4 times 6 times 3 plus, and then here we're just multiplying the entries along the diagonal. So 3 times 5 times 0. Now we're just gonna subtract it by this, so that's gonna be minus 3 times 2 times 3, and then here again that's gonna be minus 1 times 6 times 0. And by the way, the order doesn't really matter since they're multiplication, they give you the same thing. And then here minus this, so minus 4 times 5 times 7. Now we just need to simplify. So the determinant of matrix A is going to be, so 1 times 2 times 7 is just 14, plus 6 times 4 is 24 times 3, that's 72. And now these becomes just 0 since we're multiplying by 0. And now now we focus on this, so negative 3 times 2 times 3, that's gonna be 18, minus, now 4 times 5, that's gonna be 20, and then times it by 7, so 20 times 7 is negative 140. All right, and now we're just adding up. So the determinant of A is gonna be, so 14 plus 72 minus 18 minus 140, that's gonna give us negative 72. So this right here is the determinant of the matrix A. Now consider matrix B. Let's find the determinant of this matrix. So we're gonna do the Sarrus rule once again. So I'm just going to copy this, and now I'm gonna write the first two columns, which is 6, 5, 3, and then 0, 4, 2. Now that I have written down, I'm just gonna multiply them. So 6 times 4, that's gonna be 6 times 4 times 1, plus, and then, so that's 0 times 3, plus, that's 0 times 5 times 2, minus, so these are plus, by the way, and then we'll subtract it by these entries. So that's 0 times 4 times 3 minus 6 times 0 times 2 minus this diagonals. So that's 0 times 5 times 1. And now the determinant is just gonna be, so this is just 0, this is also 0, these are 0, these are 0, these are 0. They're all zeros since they're being multiplied by 0. So that leaves us with this. So 6 times 4 is just going to be 24. So that's the determinant of this matrix. And it turns out that the determinant of a triangular matrix is just going to be the product of the main diagonal, which is highlighted here. So whether it's a 2 by 2, 3 by 3, or even 4 by 4 matrix, the determinant is just the product of its main diagonal. Now, what if you don't have a 3 by 3 matrix? Like, what if you have a 4 by 4 matrix? What would you do in this situation? So in a situation like this, we need to use cofactor expansion. And I think that's the best way you could do. So we just need to like break them down into 3 by 3 matrices, and then we can use the Sarrus rule. So now for expanding, we can choose any row or column. So like for the sake of simplicity, I'll just choose the column 1. Since it has some zeros, why not? And by the way, all the numbers in the first column, they become the coefficients when you expand. So let's start with the first entry in the column. So this one right here, this eliminates the first column and the first row. So these remains untouched. So we're gonna put that there. So we have plus 1 times 7, 6, 5, 0, 2, 3, 0, 7, 5. That's the first matrix we have. And now since we're doing cofactor expansion, the signs will alternate like plus, minus, plus, and so on. So like our second one has to have a negative. Now let's focus on 8. So that's the coefficient, and 8 eliminates the first column and the second row. So these are gonna be the matrix. So we have 8 times 2, 3, 4, and then 0, 2, 3, and then 0, 7, 5. And then we'll do plus. Now for 0, it eliminates the third row and the first column, so leaving us this matrix. But since 0 is the coefficient, so anything times 0 is just going to give us 0, so we don't really need to write that. So we're good with the matrix we have. Let me just say that this is matrix C. So that means the determinant of C is basically going to be the determinant of this and the determinant of this matrix. So we can simply just use Sarrus rule. Let's find the determinant of this matrix. So let me just duplicate this. And now I'm going to write the first two columns to the right. 7, 0, 0, 6, 2, 5. Now I simply multiply these. This becomes 7 times 2 times 5 plus 6 times 3 times 0 plus 5 times 0 times 5 minus these diagonals. So that's 5 times 2 times 0 minus 7 times 3 times 7. That was a bad looking 7 minus 6 times 0 times 5. Now these are being multiplied by 0, so these are just 0, and then we focus on these. So 7 times 2 is just 14, and times 5 is just 70, minus, and now here 7 times 3 is 21, and then times 7 is going to be 147. That gives us negative 77. Okay, so let me get rid of this. So that's going to be 1 times negative 77 minus 8 times. Now we need to find the determinant of this matrix. So I'll just copy this again, and now I'll write the first two columns to the right. So 2, 0, 0, 3, 2, 7. And then we just multiply the entries along the diagonal. So this becomes 2 times 2 times 5 plus 3 times 3 times 0 plus 4 times 0 times 7 Let me move this further so I could get more space. Minus, then we'll multiply the entries along this diagonal. So that'll be 4 times 2 times 0 minus 2 times 3 times 7 minus 3 times 0 times 5. These are being multiplied by 0, so we need to cancel them out. So now we have 2 times 2 is 4 times 5. That's going to be 20 plus, so 2 times 3, so negative 2 times 3 is negative 6 times 7 is negative 42. So we'll have negative 42. That's going to give us negative 22. So our determinant will be negative 77 plus, so negative 8 times 22. So negative and negative becomes positive. So we get 176. So that's 99. So therefore, the determinant of C is 99. Number 1. Use the determinant to find out for which values of the constant k so that the given matrix A is in invertible. So we have matrix A which is given, and we need to find out the value of k which makes the matrix invertible. And there's something you need to know about invertibility. Whenever the determinant of a matrix is 0, it means the matrix has no inverse, so the matrix is not invertible. So first, let's find the determinant of A. Notice that A is a triangular matrix since it has zeros arranged in like this way. Because it's a triangular matrix, the determinant will just be the product of the main diagonal. So the determinant of A is simply going to be k times 2 times 4. So that gives us 8k. And we know that the matrix is not invertible whenever the determinant is 0. So let's put a 0 here. So 8k equals 0. So what value of k will make this thing 0? So let's just divide both sides by 8. So now we have k is equal to just 0. So when k is equal to 0, this makes the determinant equal to 0, meaning it's not invertible. So therefore we can conclude that the k can be anything except 0. So k cannot equal 0 for invertibility. Now let's do the same thing but with this matrix. So let's just rewrite this because we're going to use Sarrus rule this time because it's not a triangular matrix. So I'll just rewrite the first two column, 1k squared, that's just k, and then k squared. So we'll multiply these. So the determinant of the matrix B is going to be, so this is going to be 1 times k times 1, so that's just going to be k. And now that we have 1 times negative 1 times 1, so that's going to be negative 1. So negative 1 plus we have 1 times k squared, so that's k squared. Now we'll subtract it by these, so we have, that's going to be 1 times k, that's going to be negative k. And now here we have 1 times negative 1 times k squared, so we have, so negative times negative, that's going to be positive k squared. Minus, so here it's just going to be 1. And now let's clean things up. So k and negative k, they cancel out if you add them up, leaving us just 2k squared minus 2. And we know that the determinant of B is 0 if it's not invertible. So let's put 0. So what we'll do is, I'm going to add 2 on both sides. So that gives us 2 is equal to 2k squared. Let's divide both sides by 2. So that means k squared is equal to 1. Now we take the square root on both sides. So that gives us k is equal to plus or minus 1. So basically, for invertibility, k can be anything but -1 and -1. -1 and 1. If k is -1 and 1, that will make the determinant equal to 0, so it's not invertible. And the question was asking us, we need to find the value so that the given matrix is invertible. So yes, anything besides -1 and 1 will make the matrix invertible. Number 2, use the determinant to find out for which values of the constant lambda so that the given matrix A minus lambda I is not invertible, where I is the identity matrix. So we're given matrix A, and now we're going to subtract it by lambda I. And remember, lambda is some scalar, and we know that I is the identity matrix, so that's just diagonal 1. So 1, 1, 1, and then the rest is just 0. That's the identity matrix. It doesn't really do anything. So, and now we can find lambda I. So we're just going to multiply this identity matrix by lambda. So that's going to be lambda, 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 all in the diagonal, and then the rest is just 0. So let's find out A minus lambda I. So let me just duplicate this. So we have, that's A, and then minus lambda, 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 0, 0, 0, 0, 0, 0. Since the matrices are both like the same size, we can subtract them. So this is going to be, so 3 minus lambda, that's going to be 3 minus lambda, and then it's just going to be 5 minus 0, that's 5, and then 6. Then we have 0, and now 4 minus lambda, that's just 4 minus lambda, and then there's 2. Everything else stays the same except the diagonal term. So that's 0, 2, and then now 7 minus lambda is 7 minus lambda. That's it. Now we need to find the determinant of A minus lambda I. To find the determinant of this matrix, we can simply use Sarrus rule. So let me just copy this down. And then I'll write the first 2 column again. So 3 minus lambda, and then 0, 0. And then 5, 4 minus lambda, 2. Now that we've written it, we can multiply. So we multiply these. So the determinant is 3 minus lambda times 4 minus lambda times 7 minus lambda. And now we also multiply these ones, but since it's getting multiplied by 0, it's just 0, so we don't really need to put that. I'll move this a bit down in case we don't get space. And now we multiply this, so 6 times 0 times 2, that's also 0. We don't need to include that. So now let's multiply from this side, so that's also 0 since we have 0 here. And then we have this term, so that's 2 times 2 times 3 minus lambda, and then 5 times 0 times 7 minus lambda, that's just 0, so let's not include that because they're just 0 anyways. So let's simplify this part. We know the determinant of A minus lambda I, that's gonna be equal to, so what I'm gonna do is I'm gonna factor out 3 minus lambda. So that's 3 minus lambda, and then we times it by 4 minus, actually let's just expand. So now for this part, let's expand. So 4 times 7 is 28. And then 4 times lambda is just negative 4 lambda minus, and then lambda times 7, so that's also 7 lambda. And now we have negative lambda times negative lambda, so that's just positive lambda squared. And then we have 2 times 2 is 4. And since the matrix is not invertible, we know that the determinant is equal to 0. So let's say this, the 0 equals, so this whole equation. So 3 minus lambda times, so now let's clean up inside. So 28 minus 4 is going to be 24 minus, so negative 4 minus negative 7, that's going to be negative 11 lambda, and then plus lambda squared. So I'll just write this equation again. So we have 3 minus lambda. So I'm just going to rearrange this equation so it looks nicer. So we have lambda squared minus 11 lambda plus 24. And we can factor this quadratic equation. So we have, so our product is 24 and our sum is negative 11. So what two numbers has a sum of negative 11 but product of 24? We know it's negative 3 and negative 8. So we have 0 equals 3 minus lambda times lambda minus 3 times lambda minus 8. So therefore lambda equals 3 and lambda equals 8. So lambda with these value will make the matrix not invertible. And if you're wondering why this isn't 3 solution but only 2, it's because this and this are exactly the same thing. It's just is multiplied by a negative. And that is it for this video. I hope you found this video helpful, and please subscribe to my channel. Okay, bye.